All right, this is section 3.6, a summary of curve sketching. Today we're just going to take everything we've been doing and put it all into one. Some guidelines for analyzing the graph of a function. First thing is determine the domain and range. Second thing is determine intercepts, asymptotes, and symmetry. And the third thing is our calculus step. We're going to find the x values for which f prime of x and f double prime of x is either 0 or does not exist, and use those to find relative extrema and points of inflection. So let's dive into our first example. We have a little bit of a complicated function. I personally would probably distribute the 2 in the top, just to make my life a little easier when I find the derivative. So we're going to find our first derivative. And to do that, we use the quotient rule. I take derivative of the top, which is 4x, times the bottom unchanged, minus derivative of the bottom, which is 2x, times the top unchanged, all over the bottom squared. And now in comes a little bit of work. And I'm actually going to simplify that derivative on my whiteboard back here. So I'm going to start by distributing the 4x that I had, making it up just a little bit, 4x to the third power minus 16x, and then distribute this minus 2x, so I have minus 4x cubed plus 36x. And I like to multiply out my denominator, so that's x to the fourth minus 8x squared plus 16. Then I just simplify a little bit more. My x cubes cancel, my x's become 20x, and my denominator is x to the fourth minus 8x squared plus 16. I have my first derivative, just a tiny bit of work there. So I'll add that to my notes. I got 20x over x to the fourth power minus 8x squared plus 16. All right, then we need to find our second derivative. Well, to take our second derivative, we need to use the first derivative. And I'm going to need the quotient rule again. So derivative of the top is just 20 times the bottom unchanged, x to the fourth power minus 8x squared plus 16, minus derivative of the bottom, which is 4x cubed minus 16x, times the top unchanged, all over the bottom squared. And I'm actually going to go back to this denominator. So I can call it x squared minus 4 to the fourth power. Now I'm going to use my dry erase board here behind me, or behind the paper, to simplify that. I'm going to distribute that 20, so I get 20x to the fourth power minus 160x squared plus 320. And multiply here, I get negative 80x to the fourth power plus 320x squared. I'm going to leave my denominator in its factored form, x squared minus 4 to the fourth power. Let's see, when I combine my like terms, I get negative 60x to the fourth power. I get plus 160x squared, and I get plus 320. All over x squared minus 4 to the fourth power. And then, let's see, I think I can factor that numerator. I'm going to take out a GCF of negative 20, which leaves me 3x to the fourth minus 8x squared minus 16. And my denominator is still hanging out. And move this down a little bit. Let's factor that numerator further. Negative 20, we'll do 3x squared and x squared. To break apart 16, I'm going to go 4 and 4. So I can get minus 12 plus 4. And then I notice my x squared minus 4 cancels with one of those. So my second derivative is simplified down to negative 20 times 3x squared plus 4 over x squared minus 4 cubed. Negative 20 times 3x squared plus 4 over x squared minus 4 cubed. All right, now we can continue on. Our x-intercepts. X-intercepts, we set the numerator of the original function equal to 0. Let's see, a little side work here. 2x squared minus 18 equals 0. Add the 18 over. Divide by 2. X squared is 9, so x is positive or negative 3. So it's positive 3, 0, and negative 3, 0. For our y-intercept, we'll just plug in 0 for x. I get negative 18 over 4, which is negative 9 over 2. So 0, negative 9 over 2. Vertical asymptotes, anything that makes the denominator 0 that won't cancel with the numerator, that's positive and negative 2. So x equals 2 and x equals negative 2. Horizontal asymptotes, we had a lot of different rules for that. I can look at the leading coefficients since my degrees are the same in the numerator and denominator. I have 2 over 1, so my horizontal asymptote is y equals 2, which means that tells me my end behavior as well. On both ends, I will approach 2, so the limit as x approaches negative infinity of f of x is 2, and the limit as x approaches positive infinity of f of x is also 2. Critical numbers, numbers that make the first derivative equal 0 or make it undefined. Well, positive and negative 2 definitely still make it undefined. And x equals 0 is another critical number because it makes the numerator 0. Possible points of inflection. Well, x equals plus or minus 2 are still going to make my denominator 0 of my second derivative. And there's actually nothing that makes the numerator of the second derivative 0. So those are our only possible points of inflection. Our domain is everything but those vertical asymptotes. So we have negative infinity to negative 2, 2 to positive, negative 2 to positive 2, or 2 to infinity. And then our test intervals. We're going to make 2 different number lines here. For the first derivative, f prime, we need negative 2, 0, and positive 2, all those critical numbers. And for the second derivative, f double prime, we just need negative 2 and positive 2. So in the first derivative, if I pick a number that is less than negative 2 and plug it in, I'm going to get a negative over a positive, which is negative. If I pick a number between negative 2 and 0 and plug it into my first derivative, I get a negative over a positive, which is again a negative. If I pick a number between 0 and 2, plug it into the first derivative, I get a positive over a positive. And a number bigger than 2, I get a positive again. In my second derivative, if I plug in something less than negative 2, I get a negative over a positive, which is negative. Something between negative 2 and 2, I get a negative over a negative, which makes it positive. And something on the other side of 2, I am going to get a negative again. Now we can dive in and sketch a graph. Oops, we don't need the stuff behind it peeking out. All right. Our important numbers, we need negative 2, positive 2. I know I have vertical asymptotes at both of those, so I'm going to draw in some dotted lines for myself. I know I have a horizontal asymptote at 2, so I'm going to draw in a horizontal dotted line also. I like to start plotting with my intercepts. So negative 3, positive 3, negative 9 over 2. Right about there. All right, this tells me that my function is decreasing from negative infinity to negative 2, and then again from negative 2 to 0. And then it's increasing from 0 to 2 and 2 to infinity. Okay, so we're decreasing, increasing. I also know that I'm concave down over here, concave up in between here, and concave down again. which tells me my graph concave down and decreasing here. But remember, I can't cross that vertical asymptote. I have concave down and increasing over here, again with my asymptotes. And I just realized I did something wrong. I have my y-intercept wrong. I said it was negative 9 over 2, but now I'm realizing negative 18 over negative 4 is positive 9 over 2. So I take that all back, and instead of graphing this point down here, we're actually going to graph that point, which makes my graph actually possible. Because we are decreasing and concave up, and then increasing and concave up, but we can't cross those asymptotes. There is a very accurate sketch of our graph. All right, for our next one, we're going to start off the same way. Let's actually start with our domain. If I look at my graph, x can't be 2. So my domain is negative infinity to 2 and 2 to infinity, which tells me that I have an asymptote at x equals 2. I also know that I don't have a horizontal asymptote because the degree of the numerator is bigger than the degree of the denominator. I don't have any x-intercepts because the numerator, if I try to set that equal to 0, it doesn't factor, and quadratic formula would give me imaginary numbers. My y-intercept is going to be 0, and we get positive 4 over negative 2, so negative 2. Now let's look at our end behavior. We need the limit as x approaches negative infinity of f of x, and the limit as x approaches positive infinity of f of x. Well, if I look at this, when I do all my limit rules, I'm going to divide everything by an x. So I'm going to end up with an x on the top. If I plug in negative infinity to that, I'm going to get negative infinity. So the left side is going to go down. And if I plug in positive infinity to it, the right side is going to go up to positive infinity. Now let's dive into our derivatives. For my first derivative, I'll take the derivative of the top, which is 2x minus 2, times the bottom unchanged, so x minus 2, minus the derivative of the bottom, which is just 1, times the top unchanged, all over the bottom squared. When I simplify that, I'm just going to simplify it on here. I'm going to FOIL that first piece out. I get 2x squared minus 4x minus 2x plus 4. Distribute my second piece. I get minus x squared plus 2x minus 4 all over x minus 2 squared. Combine a little here. I get x squared minus 4x, and that's it. And I'm actually going to multiply out my denominator, x squared minus 4x plus 4. There is my first derivative. Let's see, my critical numbers here. Critical numbers. Well, 2 would make the denominator 0. And then in the numerator, I could really factor it into x times x minus 4 over x minus 2 squared. There's my factored version. So I have 0 and 4 as critical numbers as well. And just for fun, let's set up that number line right away for my test intervals for the first derivative. We need 0, 2, and 4. If I plug in something less than 0, let's say negative 1, I get a negative times a negative over a positive, which is positive. Something between 0 and 2, I get a positive times a negative over a positive. Between 2 and 4, I get a positive times a negative over a positive. And something bigger than 4, I get a positive, positive, positive. There we go. Now we find our second derivative. I take the derivative of the numerator of the first derivative. I get 2x minus 4 times the denominator, x squared minus 4x plus 4, minus the derivative of the denominator, which is 2x minus 4, times the numerator, x squared minus 4x, all over the denominator squared, which we're going to go x minus 2 to the fourth power. Multiply all this out. The second derivative becomes a lot more work, right? We get 2x cubed minus 8x squared plus 8x minus 4x squared plus 16x minus 16. And here I have to distribute that minus also, so I get minus 2x cubed plus 8x squared. Sorry, I'm going on to a second line because I was running out of space. Plus 4x squared minus 16x. And that is still all over x minus 2 to the fourth power. Combine those like terms. Let's see, my 2x cubes cancel. I have minus 8x squared minus 12x squared plus 8x squared plus 4x squared. Those all canceled too. 8x and 16x makes 24x. Minus 16x makes 8x. And for my constants, minus 16 is the only one I see. And just for fun, we're going to factor that a little. 8 times x minus 2. Because look at what that does for me. I just get 8 over x minus 2 to the third power as my second derivative. So my possible points of inflection, so I'm going to say P, POI, are just x equals 2, because that makes the second derivative undefined. So I make my number line here. This will determine my concavity. If I plug in something less than 2, I get a positive over a negative, so negative. Something greater than 2, I'm going to get a positive. All right, now we can dive into our graph. We have an asymptote at x equals positive 2, so I'll draw that in right away. I have a y-intercept at 0, negative 2. Critical numbers at 0, 2, and 4. All right, let's make a sketch. So I know that the left side is going to go down. I know that I'm going to never cross the x-axis. And I know that I'm going to cross the y-axis right here. All right, at x equals 0, I could have a max or a min. Let's see here, increasing to decreasing. I have a relative max there. And I know that at my asymptote, I can't cross the x-axis, so I better go back down. Well, I said my graph is increasing and then decreasing and concave down, so that checks out. My other part of the graph I know is decreasing then increasing, and it's concave up. And I also know that the right side has to go up. I also know that at 4, I have a relative minimum. So here, I have to figure out that coordinate though. Relative min at 4, comma, let's see, I get 16 minus 8 plus 4, which is 12, over 2. 4, 6 is my relative min. There we go. So we're decreasing and then increasing. And there is our pretty accurate sketch. All right, for our third example, let's start off with our domain. Well, the only thing I can't plug in here would be something that makes x squared plus 2, 0, which is nothing, or anything that makes x squared plus 2 less than 0. which again is nothing. So our domain is all real numbers. Which means we have no vertical asymptotes. We can find our x-intercepts. Well, our only one is going to be 0, 0, because that's what makes the numerator 0. And if I plug in 0 for y, or for x, I also get 0, making my y-intercept 0, 0. For horizontal asymptotes, remember that we have to do the limit as x approaches negative infinity and the limit as x approaches positive infinity. Let's do a little side work on those. So a reminder for the limit as x approaches negative infinity. We take everything in our function we divide by the highest power of x in the denominator. So I'm going to divide by the square root of x squared, which is really divided by an x. But the square root of x squared is always going to be a positive. And since I'm approaching negative infinity, I have to add a negative into my answer. So then a reminder that this would then become the limit as x approaches negative infinity of negative 1 over the square root of 1 plus 2 over x squared, which would become negative 1 over the square root of 1 plus, well, 2 over x squared becomes 0. So really we get negative 1. So the limit as x approaches negative infinity of f of x is negative 1. Now the limit for positive infinity is going to be the exact same thing, except that we wouldn't have that negative. So I'm just going to skip all that work and tell you it is positive 1, which means that our horizontal asymptotes are y equals 1 and y equals negative 1. All right, we have our x-intercepts, y-intercepts, domain, vertical asymptotes, horizontal asymptotes, and behavior. We're to the derivative part. We are going to find the first derivative. And for this, we take derivative of the numerator, which is 1, times the denominator, unchanged, minus derivative of the denominator, which is 1/2, times x squared plus 2 to the negative 1/2 power, times the derivative of the inside, which is 2x, still times the top unchanged, which is just x, all over the bottom squared, which becomes x squared plus 2. The simplifying part is where it gets a little tricky. We're going to keep this as square root of x squared plus 2. I'm going to cancel the 1/2 and the 2. I'm going to move this to the denominator, so I get x squared over the square root of x squared plus 2, all still over x squared plus 2. To make this so I can combine my numerator, I'm actually going to multiply by the square root of x squared plus 2 on the top and bottom, which makes this x squared plus 2 over the square root of x squared plus 2 minus x squared over the square root of x squared plus 2. And I'm just going to take that whole thing and multiply by 1 over x squared plus 2, so I don't have to write a fraction within a fraction anymore. And this will become 2 over square root of x squared plus 2 times 1 over x squared plus 2. Now we can actually combine those denominators and call that 2 over x squared plus 2 to the 3/2 power. Well, our critical numbers, anywhere that the first derivative doesn't exist or equals 0, we actually have no critical numbers. If there's no critical numbers to determine where the graph is increasing and decreasing, I basically can plug in any number. I like 0. I get a positive over a positive. This graph is always increasing. There we go. For the second derivative, believe it or not, the second derivative is a little bit easier now, because I can treat this as, right over here, 2 times x squared plus 2 to the negative 3/2 power, and then I just have to use the chain rule one time. So I bring down my exponent, I get negative 3 times x squared plus 2 to the negative 5/2 power times the derivative of the inside, which is 2x. So my derivative is negative 6x over x squared plus 2 to the negative 5/2 power. Now I do have a possible point of inflection now at x equals 0. So when I make my number line here, if I try a negative number, I get a positive over, oops, this should become a positive power now. Positive over a positive is positive. And if I plug in a positive number, I get a negative. So it is concave up and then concave down. So now we can do some graphing. I know I'm going to need a horizontal asymptote at y equals 1 and y equals negative 1. I know that my only x-intercept, or y-intercept even too, is at 0, 0. I know that the left side approaches negative 1 and the right side approaches positive 1. I know my graph is always increasing, which works out because to connect those. I know I am concave up through here and concave down through here. And there's how my graph is going to look. All right, a tricky rational exponent problem. First question is the domain. Well, the domain of this problem is all real numbers because there are no fractions in the entire problem besides the exponents. No square roots, nothing like that to worry about. My x-intercepts, well, let's see here. If I set this whole thing equal to 0, and I factor out an x to the 4/3 power, I get 2 times x to the 1/3 minus 5. So I get x equals 0. And let's see. 2x to the 1/3 power equals 5. X to the 1/3 power equals 5, halves, which would mean x equals 125 over 8. So my x-intercepts, I have 0, 0, and 125 over 8, 0. My y-intercept is 0, 0, so I'm not going to bother writing it again. We have no vertical asymptotes. Should have no horizontal asymptotes either. So we just have to deal with our end behavior. The limit as x approaches negative infinity of our function, and the limit as x approaches positive infinity. Well, if I plugged in negative infinity to this function, I get a negative infinity minus a positive infinity. Well, negative and minus, still negative infinity. If I plug in positive infinity, I get a positive infinity minus positive infinity. Now I have to decide which one's bigger exponent, so I get positive infinity. All right, now we go on to our derivative. The first derivative is going to be 10/3 x to the 2/3 power minus 20/3 x to the 1/3 power. Well, my critical numbers, similar to how we did it before for our x-intercepts, I'm going to get x equals 0. And maybe a little scratch work over here to figure out the other one. Let's see, if I factor out a 10/3 x to the 1/3 power, that leaves me x to the 1/3 power minus 2. So that gives me the x equals 0. And this one will give me x equals 8. If I set up my number line, my 0 and my 8, if I pick something less than 0 and plug it into my first derivative, I'm going to get a positive. If I plug in something between 0 and 8 to my first derivative, I'm actually going to get a negative. And something bigger than 8, I'm going to get a positive. And then we take our second derivative, and we get 20 over 9 x to the negative 1/3 minus 20 over 9 x to the negative 2/3, which we would rewrite as 20 over 9 cube root of x minus 20 over 9x to the 2/3. Possible points of inflection. We have x equals 0 again. And then a little scratch work here. If I factor out a 20, set that equals 0, 20 over 9x to the 1/3 power, that leaves me with a 1 minus 1 over x to the 1/3 power. This gives me my x equals 0 because x can't be 0. This one, let's see, we get 1 equals 1 over x to the 1/3 power. X to the 1/3 power equals 1, which means x equals 1 is another possible point of inflection. Set up our number line. We have 0 and 1. Plug in a number less than 0. Let's say a negative, obviously. I get a negative times a positive, so I get a negative. Something between 0 and 1, I get a positive times a negative here, which is a negative again. There we go. And then something bigger than 1, I get a positive and a positive, so I get positive. Now we can graph. We need 125 over 8, which is between 15 and 16. So, okay, there we go. All right, I've got a 0, 0. I've got my other x-intercept. I know it's going to be continuous because the domain's all real numbers and there are no asymptotes. I know that I am increasing until I hit 0, and then decreasing until I hit 8, and then increasing again. I know it is concave down until I hit 1. Let's make myself a little dotted line here. And then concave up. I know that the left end should go down and the right end should go up. And I know 0 and 8 are my critical numbers. I have a relative maximum at 0, a relative minimum at 8. And if I plug in 8 to my original function, I'm actually going to get negative 16, so we're just going to kind of make a dot for that. All right, so I've got increasing and concave down, decreasing concave down, decreasing concave up, and then increasing concave up, on for infinity. And there's my graph. All right, 2 more graphs for this section. This one is just a straightforward polynomial. We're going to start off the same way with our domain. The domain of any polynomial is negative infinity to infinity, and there are no asymptotes. My x-intercepts get a little tricky. I know that when I factor this, I'm going to get 0, 0. Because if I do this, if I set the whole thing equal to 0, take an x out, I get x cubed minus 12x squared plus 48x minus 64. I know I can't do factoring by grouping. I would have to use my rational zero test. So possible rational zeros, I could have 1 and 64. I could have 2, 32, 4, 16, 8, or all of those as a negative. I could look at my graph to guess. I'm going to guess that it's 4. Remember synthetic division from pre-calculus. Lets us check to see if that's a 0. Multiply, add, multiply, add, multiply, add. So leaves me with x squared minus 8x plus 16, which is x minus 4 squared. So really my whole thing factors into x times x minus 4 cubed, which gives me zeros of 0 and 4. So my other x-intercept is 4, 0. My y-intercept is 0, 0. I'll write it down. We already said no. And end behavior. This goes back to our polynomial rules. Even degree, positive leading coefficient, both ends go up, so both ends are positive infinity. Now we dive into our first derivative. Well, I get 4x cubed minus 36x squared plus 96x minus 64. To find my critical numbers, I'm going to set that equal to 0. And I'm going to factor out a GCF of 4. So the x cubed minus 9x squared plus 24x minus 16. Now I use my guess and check method again. Possible zeros are 1, 16, 2, 8, 4, or a negative version of any of those. Based on what the original function factored to, I'm going to guess 4. 1, negative 9, 24, negative 16. Let's just check to see if that works. There we go. So this factors into 4 times x minus 4 times x squared minus 5x plus 4, which makes it 4 times x minus 4 times x minus 4 times x plus 1, which means my critical numbers are x equals 4 and x equals negative 1. Test out my number line here. Pick something less than negative 1. I get a positive times a negative, 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 which makes negative. Something between negative 1 and 4, I get a positive times a negative, negative, positive, which is positive. And something bigger than 4, I have positive, 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 which is positive. And then for our second derivative, I get 12x squared minus 72x plus 96. Set that equal to 0. I'm going to factor out a 12. Leaves me x squared minus 6x plus 8, which actually factors quite nicely into x minus 4, x minus 2. So my possible points of inflection are x equals 4 and x equals 2. Put that on a number line and check. 2 and 4. Try something less than 2, I get a positive times a negative, which is positive. Between 2 and 4, I get positive, negative, positive. And bigger than 4, I get all positive. All right. No asymptotes to worry about. 2 x-intercepts to worry about. All right. Let's dive into our sketch. We're going to cross the x-axis at 0, 0, and 4, 0. I know that I have a relative minimum at x equals negative 1. If I plug that in, I actually get... Actually realized I made a mistake here. This isn't factored to a plus 1, it's a minus 1. So that should be a positive 1. Uh-oh. Let's double check between 1 and 4 again then. Let's see here. Positive, negative, negative, positive. Which still comes out as a positive. Okay. That positive 1 just threw me off a little bit. Not too bad. So if I plug in positive 1 to my original equation, I actually get negative 27. So we actually have a minimum way down there. And no relative maximum. All right. I know that the left side is going up. And I start off concave up and decreasing. So concave up, decreasing. Concave up until I hit 2. But I'm only decreasing until I hit 1. Oops. The graph isn't super smooth there, sorry. And then I start coming back up until 2. And then I gotta kind of curve the other way to make it concave down, which is the tricky part. We're still increasing and still increasing to make as good of a graph as I can draw by hand. And one final example here, a trig function. So we're going to start off with our domain. What would make the denominator 0? Well, the denominator would be 0 if sine of x is -1, which is at 3 pi over 2. So our domain is everything but 3 pi over 2. So our asymptotes, my vertical asymptotes are x equals 3 pi over 2, x equals 7 pi over 2, x equals 11 pi over 2, on and on and on and on. Every time around the unit circle. Which means my domain is negative pi over 2 to 3 pi over 2, or 3 pi over 2 to 7 pi over 2, or 7 pi over 2 to 11 pi over 2, on and on and on and on and on. Horizontal asymptotes, I actually don't have any. For intercepts, if I set cosine of x equal to 0, I get my x-intercepts. That'll be at pi over 2, 0. Can't be at 3 pi over 2 because that's an asymptote. So 5 pi over 2, 0. Can't be at 7 pi over 2, so 9 pi over 2, 0. Hopefully you're picking up on the pattern now. Y-intercepts, if I plug in 0, I get 1 over 1. My y-intercept is 0, 1. And now we start in on our derivatives. So our first derivative of the top is negative sine of x times the bottom unchanged, minus the derivative of the bottom, which is cosine of x, times the top unchanged, all over the bottom squared, which becomes negative sine of x minus sine squared of x minus cosine squared of x over 1 plus sine of x squared. Well, sine x squared, or sine squared plus cosine squared makes 1. So negative sine squared minus cosine squared makes negative 1. And minus sine of x. And now if you notice here, if I just take a negative out of the numerator, I have exactly the denominator. So my first derivative is negative 1 over 1 plus the sine of x. Which means the only critical numbers are those same asymptotes. Cn equals asymptotes. All right, they're the same. So we should be able to get an idea of the pattern. Let's put 3 pi over 2 and 7 pi over 2 on here. If I plug in a number smaller than 3 pi over 2, but bigger than negative pi over 2, let's say 0, I get negative 1 over positive 1, which is negative. Something between 3 pi over 2 and 7 pi over 2. Let's plug in 5 pi over 2. I get negative 1 over 1 plus 1, which is still a negative. Something bigger than 7 pi over 2, but smaller than 11 pi over 2. Let's try 9 pi over 2. Hey, guess what? I still get a negative. This function is decreasing everywhere. No relative maxes or mins. And then for our second derivative, we take the derivative of the top, which is 0, times the bottom unchanged, minus derivative of the bottom, which is cosine of x, times the top, all over the bottom squared. So our second derivative is cosine of x over 1 plus sine of x squared. Very similar to the original function. Guess what? Our possible points of inflection are the same as our domain, or our asymptotes, and the x-intercepts. I could possibly change inflection, or possibly have points of inflection at the asymptotes or the intercepts. So we're just going to do a simple little section here. We're going to start at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. All right, something to the left of pi over 2. Let's try 0. I get 1 over 1, which is positive. something between pi over 2 and 3 pi over 2, I like pi. I get negative 1 over a positive, so I get negative. Between 3 pi over 2 and 5 pi over 2 is 2 pi, so we're going to get a positive, negative, positive. It'll always follow that pattern now. So now for our graph. I'm going to draw notches for every pi over 2. Okay. I'm going to graph my x-intercepts first. Pi over 2, 2, 3, 4, 5 pi over 2, which means negative 3 pi over 2. There we go. I have asymptotes at 3 pi over 2, which is here. And I'll have an asymptote at negative pi over 2, which is here. Also have one over here because of the way I drew my graph. All right, we know that the graph is always decreasing. We know that it goes concave up, concave down, and it switches at those x-intercepts. Concave up, concave down. Looks very similar to my tangent function. And notice also that my graph went through the point 0, 1, which is exactly what I needed. And there's my graph.